Our next talk this morning is by Karlsson, who is going to tell us about a cat zero alternative for amenable groups.
Right, thank you very much. So, I'm very grateful to the organizers for inviting me to this great institute, this great program, great workshop. So I've seen Misha Kapovic many times over the years. I always enjoyed his company greatly and benefited from his many insightful remarks. And as has been said many times, and can be seen from this workshop, his interests and contributions are very broad and deep. Okay, the name of the workshop is Actions on Graphs and Metric Spaces. So gamma will always denote the finitely generated group. And so it acts by isometry on itself, and also the way it acts on other metric spaces can often be a way of studying this group. And one particular thing is fixed points you're interested in. So I'll use the following notation. So gamma has property F for fixed by definition, and then C some class. I will change this class of spaces. If whenever gamma acts on, so by isometry always, on metric space, X in this collection, this family, then whenever it acts, it has a global, and sometimes I will leave out global, fixed point. It has a fixed point, which means, i.e., with some point of X, every element of the group fixes this element. Okay. So the first, and that's also in the abstract of the workshop, is mentioned directly, Serre's work on trees. So the first type of this property maybe is Serre's, so from the 70s property, FA, where A stands for trees because it's arbre in French. And so this is related to, as he and Bas showed with the amalgamation products and H&N extension. And another one is property FH, where H is a Hilbert space. And this has particular interest also because this is turned out to be equivalent to property T for Karlsson. And the equivalence, I think, maybe is due to the Delorme which I did. So this also have a special meaning. And then there's Alperin and Watanabe. Notice that FH implies FA, because if you act on a tree, you can build an action on a Hilbert space. But many of you know this much better than me, because it extends then to Cassio-Q complexes. Okay, then maybe with geometric group theory, the rise from the 90s. So these H, Hilbert space and trees, they are cat zero spaces. And so you can also consider, and that was important, was introduced by Karlsson and Volkmann, for the real trees, which are one-dimensional cat zero spaces. I will come back to this later. And also there were studies of finding fixed points of certain actions of semi-simple type, that every isometry is either hyperbolic or elliptic, so no parabolics, which since they act on trees, those are all isometries. And also if you have a co-compact proper action on a cat zero space, they are semi-simple, so they have particular interest. And of course, there are many papers, but one is by Kapovic-Lev that I remember, and And in general, many of these works, or some of these works, consider lattice, higher rank lattices, because they're known to have property not being an amalgam from this work, and extensions to the mapping class groups and automorphisms and trees and so on, which unfortunately I will not say much about. But just maybe to finish this introduction, so far in 2003, I think, okay, so what about trees? What about extending it to higher cat-zero complexes? And so he introduced property F-A-N, where n is the dimension, and also Bridson. But this, one can then consider a strong property F-A-N, meaning that acting on cat-zero spaces of n dimension, with only allowing semi-simple, so no parabolic edge. So, okay, so that's just some points of, I don't know if it's called history, but some context. Now, with here, we will look at, so here, we'll consider FCN. So what is CN? So I invented it just, we invented it, I mean. So what is field? Okay, so we say gamma has, so I write it maybe one more time, property FCN, if whenever it acts on an n-dimensional, in some geometric dimension, there are several notional dimensions. There's an old paper by Bruce Klein that sorts out the various definitions. N-dimensional complete cat-zero space. It has a fixed point, or global fixed point. So I just wrote this in detail. So the Cn stands for n-dimensional, or maybe perhaps I should say at most n-dimensional. Of course, if you add one dimension, if you act on a say n dimensional, of course you act on n plus one dimension because you just add one axis and then you act like this. So it's obvious that you have the following diagram, maybe. I don't know if it's too simple. And so you have the dimension going up. Here you would have cells. Here you would have one-dimensional case. And then you can consider an F. So that's FC1. The color was not here. I'll call this. So FC2. So if you can't act on two-dimensional cat-zero spaces, and 3, etc. Okay. So, and on the other, you have Hilbert spaces. And I would consider also Euclidean. Okay, that's only one space, but fixed point whenever you act on the real line. So of course, you have implication this way. And F2, Euclidean plane, acting by isometry in Euclidean plane without fixing a point, always having a fixed point, etc. And so you have all these trivial implications. And then you have the only non-trivial one going this way, which I mentioned previously. Okay. So we have. So there's a recent paper by. I mean, I'm sure there are other papers, but there's a nice paper published this year by Martin about, and he defines fixed dimensional. He considers exactly this property for certain, and the game with this n is with other works, also with the Helly type theorem, so with intersection of convex sets and playing that with dimensions. So, for example, he proves just a sample, or an important one, but it contains many things in this paper. So, he defines that fixed. For any gamma, he considers fixed dimensions, which is the highest dimension for which you can act with that big one. So one sample result, which I will not speak about, but I'll just just to mention a bit of flavor. Okay, so that's a kind of introduction. Maybe I could. Probably everyone knows the cat zero definition, but it's maybe right there. So a geodesic and complete metric space is cat zero. If whenever you take 3 points, so they should exist geodesics, and they will be unique. By Euclidean geometry, so for any such triangle, there is so this is Euclidean space, 2-dimensional, with the corresponding length. And now it insists that when you have this, you have a map from the sides of this triangle, and you insist that this should be non-expansive. So that's one definition. Okay, definitional dimension, maybe I don't skip for now at least. So then I'm ready to formulate the main result. Okay. So the dimension we use is the one mapping a barycentric simplicism to how many dimensions you can map without that it degenerates. Okay, if this was the introduction, this is section 2, main results. Okay, theorem. So there was an earlier version that's appearing this year by Hirayashi Sek and myself, and the UV group, but then the more general is in joint work and in progress by these collaborators. So this appears now at some point. And it says, so let gamma be a finitely generated amenable group. So one definition is that whenever it acts in a compact set, it has a invariant measure. A minimal group or Fellner set condition. And take some dimensions, integer n. So I mean, so it's a bit in contrast with the work I've been talking about. We have studied important groups in geometric group theory. So, but here's amenable groups, which are also, of course, important. So then you have the following dichotomy or alternative, that either gamma has f's, it fixes a point whenever it acts on at most n-dimensional cat zero space, or gamma acts on Euclidean space with no fixed point, no global fixed point. Okay, that's the main thing. So in terms of this diagram, so that shows that for amenable, you have equalities. So if you can act on cat zero, then you can act on Euclid. So if you can't act on this, you can't act on Euclid for amenable. And so it's, by the way, it's known from Gromov and also Cheritz Valette that any amenable group they don't have this. So how do I explain? They are not contained. Okay.
Amenable intersection T is finite groups.
Oh yeah, something, yeah. 6. So they act on.
Properly.
Oh yeah, unless they are finite, yeah.
They act properly. They act properly on amenable space.
Excuse me?
Amenable groups act properly.
AT
Yeah,
amenable.
Yes. Yeah, HTML. Okay, so. Yeah, so I mean, so I wanted to contrast that with that they do act on Hilbert space, but they don't. I mean, then, yeah, you can't extend this to infinite dimensions. Okay, so this has some corollaries and maybe some remarks.
Excuse me? So
Yeah.
acting on En with no global fixed point, is this the same as having a virtually abelian quotient?
No, having no. Okay, I have to think about it. Okay. Maybe somebody smarter can answer it. I had to think about it. Sorry. So, remarks. Okay, I already said that amenable groups do act on Hilbert spaces, so I don't have to say that again. So, and also notice that, so, if gamma doesn't have this fixed point property for some n, and it's enough with n, then it has an infinite image, finite dimensional linear representation, since the affine linear group, I mean the ones that preserve, they are obviously a matrix. So that's one remark. Okay, now for corollary. So relating to this property, we can say that in the case of amenable groups, it doesn't matter if you allow parabolics, because then strong FAN would imply FCN. The stronger property. And the proof is then, okay, FAN, because it's a Euclidean has only semi-simple isometry, so yes, strong FN implies.
What was AN again?
Oh, sorry, yeah. AN comes from that you're thinking of as extending cells FA to higher dimensions. And but then what this means is whenever you act on a cat zero space of n dimension, but without parabolics, you have a fixed point. But here this shows that you don't need this condition, because this implies Euclidean, and then the theorem implies that you have. I mean, if you can't act on Euclidean, you can't act on zero. Okay, now I can erase this. Okay, so now another corollary. The following. This more interesting. Is every finitely generated amenable group, amenable torsion group. That means that every element has finite order. Has FCN for every n. It can never act on a cat zero space. And such groups exist. I mean, infinite such groups exist, but that was a non-trivial. I mean, from Bernstein's question to Golod in the 60s, I recommend the paper by Denis Ossian on that topic. I mean, there's an important chapter of algebra. And that such infinite groups exist. Now,
They're not amenable.
sorry?
Those in my paper are not amenable.
They're not. Okay, I should have read the. But yeah, exactly. But they exist. I mean. So perhaps the most well-known and famous the Gregor-Schuk's groups of sub-exponential growth. So because they're side-based to growth, they are amenable, and because they are torsion group by definition. And more general, so-called branch groups, which are automorphism groups of rooted trees. So I mean, it has this global fixed point rate, as it should. Because they are not linear. Many they are not linear. That's sounding Gregor-Schuk and Aber, from what I understand. And also they're often just infinite. And Dennis can correct me if I'm wrong. So it means that we heard about the other day. So they have, but this means that they are not. They can't. So I mean, this implies that they can't have f in n, and that implies by the theorem that they also. So there are many other groups. So, but more general, without unfortunately, or yeah, for this corollary, we can't remove amenable. But I guess that's a well-known question in geometric group theory. Old one, for example, appeared. And we started maybe from the paper of Svensson. It appeared in the influential problem list of Bestrina and in other places. And so it's a well-known problem. But there is one important from Misha Sergeyev from 90s, finite generated torsion group. I improvised the notation for Cat-zero cube complexes. Finite dimension. On the other hand, infinite dimension, they can act. There's the Burnside groups, for example. The Damien Osaida's paper showed such actions. Also, Serre, by the way, showed that you can't remove these finite generators. You can't remove this. You have to have the finite dimension. But yeah, I would like to remove this, but I can't. And that seems to be difficult because here's one partial result in the general case without amenable by Norin, Osaida, Petitsky. And 22, because so they show that torsion group finite torsion have property FC in dimension 2, but then I think its complex is not quite fully general Cat-zero. But this is a serious work. It's 45 pages published in Duke, so that's a serious. Okay, one other corollary or the main result would be the following.
Just to make sure, when you say that gamma acts on the Euclidean space, you mean an affine action, right?
Oh yeah, by isometry.
By isometry.
Yeah, isometry. Yeah, all actions here are by isometry, at least so far. Yeah.
For the Cat-zero cube complexes, though, they have to preserve the cubical structure? Or just has to be
that's
isometry?
now here. This is not really my, but I don't know. Somebody can. You asking about this?
Yeah, I was just wondering if in that case you insist on them preserving the cubical structure or just isometries.
Oh, that's you have to ask somebody else. Yeah. Yeah.
So probably cubical isometry.
Oh, that's what I'm assuming there.
It has to preserve the cubical.
I would guess.
Oh, okay. I didn't know that there was this subtle difference. Okay, good. Okay, okay, here's another corollary. So that's any finitely generated simple amenable group has property FCN for every n. So they can't act on a finite dimensional system. Okay, so that's a proof. Yeah, proof for this. So if not, it acts on Euclidean space. But now it's simple, so it means that the group has no normal subgroup, right? So that this action has to be either trivial, so it means that gamma is linear in this case, and that means there's the Tits alternative. It shows that there must be, since it's amenable, it's virtually solvable. And that solvable and simple doesn't go together. It probably means that gamma is a cyclic group of P, order P. But that's a finite group. You take the barycenter or circle center, something like that, and that fixes a point. So that's a contradiction. And so it's the end of that. And again, it's a highly non-trivial fact that this exists. But they do since, well, they've always existed. but known to exist. It's, if I'm correct, this is first, I think there was a proposition by Gigashot, that was proved in the famous paper by Zhushenko and Monod. And there is also other construction by Matlebon and Nekashevich. That such groups exist. I mean, infinite. Okay, so now let's see if we can prove the main theorem. Do you have any questions? Oh yeah, here's one other possibility, but we didn't look at it. But there was a work with Farley on Thomson, because maybe one can use this for subgroups. So even if you prefer, if the amenable group is not your taste, maybe you have subgroups that are amenable inside the group. I don't know. Or you have Thomson's group F, and his idea was, I mean, in some paper, was to try to, because he got a proper fixed point free action on a proper, unfortunately, infinite dimension, cat zero. I think it's, yes. And so fixed point free. Now he wanted to play out that with the Adams-Ballman theorem that can more or less come to soon, that if he could also show that so Adams-Ballman says that there must, when there's a proper, there must be either, when the group is amenable, either invariant flat half plane, that's right, invariant flat space, flat Euclidean space, or that includes the zero dimensional, which is the fixed point, or there's a fixed point at infinity. But unfortunately, this has fixed point at infinity. But now with these two, we don't need the fixed point at infinity. It's fine if you have it. And so I think, at least when you pass to the commutative subgroup, we can't act on Euclidean space. So if you could have changed this, you would have known, you could imply from the theorem that it would be non-amenable. But just to be clear, we can't do this. As usual. It's almost a proof, but as usual, not a proof.
But I mean, maybe it's known not to have any actions on finite dimensional cube, the right subgroup. Thomson's group.
It's known
Actions
to
on
have what?
finite-dimensional. I mean, can it have actions of finite-dimensional cube complexes
Yeah,
without fixed points?
yeah, but we would like. But you would like. Yeah, I have to figure out again the logic, but basically, yeah, we have this problem. But so yeah. So what you say? Yeah, if you can remove the cube complex from what you just said, you would know it's not amenable. No, it's yeah. I think because that would contradict this statement. Okay. Okay, so let's see the proof for the main theorem. Okay, so we start out with a finite generator group, gamma. Okay, it's a bit redundant, but the S is a finite generating set, and it's amenable. And we say that it has, if it can't act in Euclidean space of dimension n or lower. And now, in seeking a contradiction, we say we have found an action by isommetry on a cat zero space of dimension at most. Why? Without fixed point, which is the theorem says it's not possible without fixed point. I mean, that's what we want to prove. Now we're seeking contradiction. Okay, so in particular, it doesn't. This has no homomorphisms to R. In particular, we'll see. Okay, so one main ingredient is following extension of the Burger-Schroeder theorem, or an extension of the Adams-Ballman, but to finite-dimensional instead of proper. So that's the Capras-Liebig theorem. Which is the same conclusion, it says that X being not necessarily proper, but finite dimensional, or they have telescopic dimension, but we will not go into it. Complete, of course, cat zero space. You have gamma amenable. Then you have that gamma acts on a space, say, Y. Sorry, X. Okay, so let's stick with the same. X, and it acts on X by isometry. Okay, then it's not a mutually exclusive thing, like in contrast to the theorem there, but it says then either there exists an invariant flat, which is a totally geodesic embedded Euclidean subspace, or and that could involve a fixed point, or there's a fixed point at infinity. Fixed point at the generalized boundary at infinity, the visual boundary. So that means that all the subset, the equivalence classes of geodesic rays. Notice a priori when the X is not a proper cat zero space, this might be an empty set. A priori, you could have a space which is like this tree, but there are no rays, so the boundary would be empty. Actually, the proof uses, so I'm happy about that, because they use a beautiful, the use is beautiful of our result, my rules and mine, that I presented here when I was here the first time 25 years ago. So, and because they want to minimize the convex function and the gradient flow in order to get this exact. Because unless you have so this uses Boltzmann function. Unless you have this flat that is the minima, you must have convex sets with the minima escaping you. But in general, it may not exist. But if you have this non-expansive and the drift or the displacement is positive, then our result implies that they exist. The old one with the by that exists excite and minimize it to this functional, and that's how they get this point, which a priori, as I said, doesn't necessarily exist. Since we talked about broad interest, it's maybe worth mentioning that, if I made a little parenthesis, there's this in complex geometries, there's the Calabi problem that asks if every Kähler manifold has one metric Kähler metric in the same class of constant scalar curvature. And then there's this Calabi flow, which is a bit like a Ricci flow. And that flow is a non-expansive flow on cat zero space. So this type of arguments also can be applied for some parts of that. But I like non-expansive and I like cat zero space. So even if you are just interested in isometry thing, you will be led into non-expansive. Okay, I have to focus. Back in here. Okay, so we have the Kapras-Liczak term. So what does it tell us? It tells us that we must be in the case, under the hypothesis we made, we now have a fixed point at infinity. Right? Since we started out by gamma amenable, okay? Not having this, so we have no flat. So the only that remains is that it has a fixed point at infinity. Okay, so we get psi at infinity. I have to make sure what matter I have. So the picture is maybe like this. And you have a base point with psi, and so you have that geodesic ray that represents this. Equivalence class, if you start from x0, that geodesic, and then I have another own page. And okay, we should do one thing before maybe this, but the picture will be correct, just for a different space. So we'll consider the displacement minimized over all of y. We take the maximum of this finite generating set, and you see how it's translated. How does it move y? And then you try to minimize this. And so it, of course, since it's a positive, of course it's a non-positive number. But it's like for isometries, it's a bit annoying, or at least this problem that I said, or this thing. You want it to be positive. But there's a way of doing that we learned from a paper by Bourdon on LP spaces. But Cornelia tells me that this is, and he probably refers also to Gromov, and also Shalom, so maybe the other people. The following, that there exists then some sequence of points, y, and numbers, so that you can consider an ultra limit. So you take a non-principled ultra filter on the natural numbers, you can take this limit. Now, okay, these I will not go into, but if, by the way, to everything I say, the excellent reference is the Dr. Kapovich book, Geometric Theories. I recommend this. And everything, and they have a chapter on this also. Now, so that's not so obvious, this argument, but this makes that, okay, that when we pass to z, it has the effect, this scaling, that now this number is strictly positive. And then there's one sees that the dimension hasn't gone up. That's, for example, in the paper by Liczak. And okay, now I'm in this picture. Now we have an action and we have z. So now I apply capacity check to z. That's better. That's to remove. That was a bit too fast. So now we have this picture. Then one looks at the Boltzmann function. Found in 1930s, but it goes back to 19th century math also. Who wants to find it with Poisson kernel? If I have time, I'll come back to this more. And so this gives you these Horror spheres. And because your group fixes this point, it fixes this Boltzmann function, and so it translates these levels. But since the group doesn't act on on the Euclidean space, it needs to preserve this. So if you act your group, it will be only here. This means that you can now take another outer limit, or there's another way of doing it, look at this transfer space. So you push this, you look at now this horse here, and kind of take the limit of it, and that will give you some kind of limit. And that will be a cat-zero space, there will be pseudo distance, but you quotient out, but then alternatively, you take, say, Z1 to be this space, at the limit of, with base points along the geodesic. And then one can see that these splits, by the usual splitting theorem, one Euclidean factor. And so what we achieve is now, moreover, okay, what we achieve, so we have now an action. We have now action, of course, by itself, by gamma on these two. Okay, so I'm changing space all the time. But I'm changing space, but it's because I'm going into a contradiction. So I'm not, in some sense, we are not finding the fixed point in the space we started with. It's only implicitly, I'm not looking at the fixed point here, but we'll push it to get the contradiction. Because what is good about this is that we have decreased the dimension by 1. And also, it's obvious to see, once you go through what this outer limit does, that the displacement function of this is the same. And that was positive. And now I think it's clear what you do. You continue this, because you peel off the dimensions one after the other. And that, in the end, will result in, because you have that flat subspace. So it will, so you repeat, and it's a finite dimension, so at some point you get the space that's R, that gamma acts on. Okay, but gamma acts on this, but all the time delta was positive, so there's no fixed point. This always guarantees there's no fixed point, so we apply, when I say repeat, we use, again, capacity check to get, there's no flat, right? No fixed point, no flat. The fixed point is at infinity, and then you do the scaling again, or limit. And so, but that was assumed to have no fixed point on either end. Smaller Euclidean space, so there's a contradiction. And so therefore, we must have had a fixed point. Okay. So any questions?
So where have you used amenability other than just from the
only this. And I think it's a good remark, because if you knew some other way, I mean, suppose you knew just the conclusion of the capacity, then you could do the same. So you're right. So there's, let's see. Yeah, there's no amenability apart from that. So if you had a similar statement, which is conceivable that you have a group that can't act on, okay, but a priori, it could be one direction too.
Does the same argument work for like a finite telescope dimension?
Excuse me?
It's the same, yeah, here. So
Yeah, telescope, finite telescope.
Finite telescope
Yeah.
dimension.
Yeah, I guess so, yeah. So you mean I could put finite telescope? I could use
That's my question, yeah.
the telescope dimension here.
Yes, is that true? Or not?
Yeah. Yeah, probably, but I'm a bit worried about it.
Infinitely.
And where did you use finite generation?
Finite generation.
Well, we've taken a max over.
Yes, exactly. Yeah.
Okay.
Thanks. Any other question? I'll just send it to the audience. Yeah, Dennis.
So, can't you extract a quasimorphism from this existence of a fixed point on the boundary? And then if you have an amenable group and it has a quasimorphism, then it must be, then you get a homomorphism to Z, and you get it in position.
Okay, I don't see it, but I don't see it, but because we already use that. You don't have that direction. Which the Bussmann would give you homomorphism, but now you're on this horror level that later will scale. So I would have to think about that. Yeah. Okay. Now to the last thing I want to say. So the last bit is for those who don't care about Katsio space. Maybe you should keep silent here in this conference, but still, respect to all types of views. Then I can still give you a fixed point. At least not for a group, but for individuals. Okay, so it's the following. The isometry of a metric space X has a fixed point. It reminds me of once a talk I intended by Sullivan. He got pressed, what is this? Is this a statement or a conjecture? He says, it's just a sentence. Okay, this is a sentence. So obviously this is a ridiculous sentence because it's false. I mean, for example, I didn't say that it was complete metric. So if you have fixed point, take them away. Then, okay, where's your fixed point now? Second thing, if you have translations, any translation, there is no fixed point because everyone's moved. Okay, that's you can have a compact example. Take the circle. Next to the circle, you have a rigid rotation. You don't have a fixed point. But the statement, there is a canonical weak type of compactification. So it's canonical, so your isometry extends to this thing. I will say what it is. And with that, it becomes a true statement. It's not only a sentence. And so, what is E? E is something I don't understand so fully, but it's the injective hat. So that's, you can think of, at least that's what I think. If you have the circle, the problem with the circle is not convex. So this is the way of kind of filling it. Now, you don't need it. You don't need, so I could have formulated it without it, if saying that if X, assuming instead that X has conical bicombing. I think the word comes from Thurston, or it's also by Takahashi, and also Bussmann used the word distinguished geodesic. So this is kind of choice. If you have many geodesic between points, it's a special choice. so that you have the convexity, almost like cat zero. So this is, for example, cat zero, just with a unique geodesic, or Banach spaces with lines as being your bicoming, or injective spaces. And that's why the injective hull will fix. If your X doesn't have a bicoming, they can go to the injective hull or hyperconvex space. You get this, and convex subsets, and there are other spaces. Okay, then I need to explain this bar, right? And that's also a well-known thing, or at least a variant of it. Anyway, it's not due to me in any way. I call it. Okay, so now I explain this. It's the metric compactification, often called Horo spherical closure boundaries. And so you fix X0. I think of it as the metric dual space, because you associate to every point a functional, as Banach would say. And so on. So the morphisms in this category, the most natural ones are non-expansive maps. So isomorphism or isometry. You map X to a certain non-expansive function, namely. So essentially this. So think of in vector spaces. If you have a vector, you get a linear function by just fixing one. I like to normalize to be zero at the base point, which nothing depends on this. And now you take the topology of pointwise convergence to take the closure of this. So this is clearly continuous and injective. It's easy to see. And this is compact by Tikhonov's theorem. So I think of this as the weak topology, and this is the analog of Banach-Kaloglu. Also, one can see a Han-Banach statement for this. And the great, so what is this? This is limits of this, right? But we already saw those here. So the nicest one are the Busemann function. But in general, there are many more. But spaces like cat zero spaces, they're all, so they're kind of reflexive spaces. That's why they have a kind of weak type of right here, compactness. Anyway, so you can say a lot about this analogy with function analysis. But so okay, I don't have time maybe, but this kind of fixes many, so to speak, many counterexamples in function analysis in other places. For example, the von Neumann ergodic theorem that he was very happy about, the mean ergodic theorem. It's not considered a very difficult theorem these days, but it's just I view it's just a fixed point theorem. You apply it to this transformation, and then you see if you, and then the traditional statement is this. This goes to E. Okay, you can say this is the projection of the U invariant vectors. But this is just a. Okay, so this is for Hilbert space. So X is Hilbert, but it's known since a long time that it's not true for L1, L infinity, and so on. You don't have this. But this thing is always true. So there you can get a precise statement of mean ergodic. So maybe I shouldn't speak about that. But I give you a small example. Let's see. But I like that anecdote that von Neumann is supposed to have said to young Nash with his Nash equilibrium. Probably he was a little bit jealous that, oh, that's just a fixed point theorem. Okay, here's a little small, it's a too simple example, so I'm sure he wouldn't have wanted his name written, but anyway, I write his name, Kakutani, because he has many other examples that are more interesting. So consider the following vector space, so all sequences that tend to 0. There you have the supremum norm. Okay, and so that becomes a Banach space. Now consider the map that takes the sequence, this to, so it does a shift. It's an affine map, you add 1. Now these maps, the unit ball to itself, unit ball to itself. So of course it's isometric, it's a continuous map, so in particular continuous. So of course, Brouwer doesn't apply because it's infinite dimensional. And you see even that it maps in the first step, it maps into the sphere, so to speak, so which is not possible. That's one of the proof how it goes. So, but this has no fixed point. So Brouwer is false even for isometries, you could say. Because if it had a fixed point, of course, if you had a fixed point, you can iterate it. But that shows that you need to have 1 in the first quarter, 1 in the second quarter, 1 in the third quarter, in every quarter. But this doesn't belong to the space, so there is no fixed point. But this theorem says there is a fixed point. And so the fixed point is, or at least 1, is the following. But I mean, this is a small illustration. I don't say that that's the. But yeah, it's for any metric space. So it's, okay, yeah, I'm talking about Banach space. And that's an element, or what I like to call metric functions. I like to call it. So that's an element in my notation. And that's fixed because h of x is h of x, I think minus 1. And if you look how so isometries act by homomorphism on this. They act like this, like we had in our picture, which translates the horizontal. It's just that it's true, not without cat zero space. And I like this fact that, okay, Bussmann functions is a tool in, we heard it in Beatrice's talk here, and also if you speak to people on non-negative curvature, they say also it's important tool with the Chiga-Yomo theorem, and Yao, and so on. The splitting of you have a geodesic, you take Bussmann function. But in fact, it's a useful tool in any, without curvature. So, okay, so thanks, Beatrice.
Questions?
So Shannon defined this property HFD for amenable groups, saying that you have non-vanishing first cohomology for some finite dimensional representation. Isn't this just the second part in your dichotomy? I mean, the action on the Euclidean space, you never said it, but it's affine isometric action, right?
Yes, yes, yes.
Yeah. So these
but
are
that's
just
infinite dimensions, no?
HFD means you have a finite dimensional representation.
Oh, sorry.
So you have affine isometric action, these are one co-cycles, and fixed point means this is still in homology, so I think it's just property HFD of Shannon.
Yeah.
The second part in the dichotomy.
Oh, it's by isometry?
Yeah.
Okay, and so...
And he proved that polycyclic groups have this property, and he has this he has a speculation. I mean, I'm not sure he would call it conjecture, but he says this in the paper that maybe these are exactly the amenable groups with finite rational topological dimension. So it's interesting. You describe somehow the counterpart of HFD.
Oh, thanks for reminding me. I had forgotten about it. Yeah. So that maybe we can give it more corollaries. Thanks.
Yeah, I think so.
Thanks for the remark.
More questions?
So, for injective holes, is the conical bicoming the relation between it and the Horror function factorification? A version of a closure defined using the conical bicoming.
I'm not sure exactly I understood, but so if your X doesn't have conical bicoming, you need to pass to the injective hull.
Which has one.
Which has one,
And
exactly.
then you take its Horror function compactification.
Yeah, exactly, yeah.
Is there a compactification you can take that's defined in terms of the conical bicoming?
Oh yeah, so you like this, right? The kind of this geodesics, right? So that's how I'm thinking. I would think no, but I don't know for sure. But you see there, I'm thinking as this as kind of the dual space. So I'm passing to, because geodesics are maps this way, but dual metric functional in my terminal is this way. And here we have this compactification, but it's very natural, like your question, if I understood correctly, to consider what about this boundary, or if there's, basically I don't know, I suspect, of course, in cat zero is kind of, as I said, reflexive, so then it's fine, but for Banach spaces, if I had, actually, I know I don't have time to think. I think, no, but please think about it and tell me what to do.
More questions? Okay, if not, let's thank Anders again.